All right. So last week we started talking about FPGAs as another point in the spectrum between programmability and performance and efficiency. Just like what we did with GPUs, this week we'll spend a little bit of time talking about the programming models and the programming languages and the usage models of FPGAs. And then we'll spend a couple of lectures, one or two lectures, on the architectural impact of how we can better program these things and on good programming approaches and methodologies and data structures for making the best use out of your FPGA system. So yes, let's get started. So last lecture, we talked about what FPGAs are and hopefully in what contexts do these things do well in. To recap a little bit, the programming model for FPGAs is actually at a high level very similar to GPUs, at least in the context of PCI-attached accelerator cards, which you would use much like you would use GPUs. So FPGAs, when you build FPGA accelerators and software that uses them, the accelerated application now should include both software and hardware portions. The software that is running on the running on the host side, on the host CPU, for example, needs to be accelerator aware. It needs to be aware that the accelerator exists, and it is typically responsible for sending and receiving data to the accelerator, and then sending control signals to the accelerator to basically say, you should start processing, you should stop processing, how many pieces of data I sent you. These kind of high-level informations are transferred to the hardware from the accelerator-aware software. And its counterpart is the accelerator itself, which is programmed onto the FPGA, which does the heavy lifting. Typically, these things are, we mentioned briefly in the previous lecture, typically these things are kind of dumb processing engines. Of course, you have a wide array of choices on how to design these things, but at least for the purpose of this 1 or 2 week long sub-lecture on FPGAs, we're going to be focusing mostly on the dumb engine aspect of FPGAs. And the thing is, one of the parts that puts the FPGAs on the spectrum, the farther in the spectrum of programmability versus performance spectrum compared to GPUs, is that typically, at least at this point in time, these two components are programmed using different programming languages, different tool chains, et cetera, et cetera. There's a lot of effort to try to merge these two things together with varied success. But at least in the market right now, in the industry right now, the two tool chains are pretty much siloed from each other. They're different languages, different tool chains, different compilers, typically even different companies, et cetera, et cetera. There are some similarities with GPU programming, as you probably noticed already. GPUs do also execute explicitly implemented kernels, communicating with host software, typically over PCIe. But the difference is, at least in the NVIDIA CUDA example, and also in the OpenCL example, there is a somewhat unified programming language, which is CUDA-C. If you write CUDA-C and you create a file with an extension .cu, and then you feed it to NVCC, it turns into a single binary file, which includes both the kernel and the host software. When you run the single binary file in a GPU installed machine, that single binary executable is responsible for transferring the kernel to the GPU. It is responsible for transferring the data back and forth, et cetera, et cetera. It does everything for you. Unfortunately, there doesn't seem to be that level of support in the FPGA area quite yet, although there's a bunch of companies who are working on it. For example, if you write OpenCL code, it is still, you can use it just like you would use a GPU. But I will get into a little bit about why that support is not quite ready yet, unfortunately. Another difference is that with GPUs, the kernel is also software. A GPU kernel is also software, although it is a explicitly parallel, massively parallel piece of software, but the kernel is still software running on a semi-general purpose cluster of processors on the GPU chip. Whereas the FPGA kernel is typically implementing its own hardware from ground up, as opposed to running, depending on and running on a pre-built general purpose processor. The FPGA kernel is implementing also its processor, so to speak, some processing engine. We'll get into details progressively. And if you want to talk about the programming languages and tool chains for programming FPGAs, the languages and tools typically overlap a lot with ASIC, application-specific integrated circuits, and VLSI design, which are tools that are used to eventually actually fab out, tape out chips, physical chips you would get from a fab plant. And these kind of tools scare people because they're very complicated, they're oftentimes very expensive, et cetera, et cetera. But FPGAs make life a little bit more easier than if you went straight to ASICs, and we're also going to talk about that in a bit. So FPGAs for acceleration is typically programmed with one of two programming languages and models, which is a little bit deviating from the traditional ASIC and VLSI design path a little bit. But yeah, one of two languages, although there are probably a few more languages between the spectrum of between these two things. But in general, I think it's pretty safe to say most languages and tool chains fall into one of two categories. The first one is the larger share of the pie, is the category of hardware description languages, or HDLs, which are also sometimes called, and it's not strictly true to say that these two are the same things, but with the purpose of providing a high-level introduction, I'm just going to use them kind of interchangeably. Hardware description languages, which are also what is called registered transfer level languages. In the next slide, we're going to next slide, we're going to talk about what exactly this means. Basically, this is the low-level languages, the assembly language of the hardware design world. The other category is the high-level languages, sometimes called high-level synthesis languages, which are compilers and tool chains and things like that, which translate software languages such as C or OpenCL even to RTL. So basically, this is stacked on top of the other one. You program a high-level language, gets translated to RTL, and the RTL gets actually synthesized to hardware. And I'd like to emphasize again that we are nearing the end of the performance/programmability spectrum at this point. We are nearing the point in which the programmability is the most difficult, but potentially with the only exception being maybe ASIC design. But we are also reaching kind of close to the limit of what you can get in terms of performance and power efficiency from underlying silicon. So yeah, the least ease of programming, but the most amount of performance and power efficiency. So I guess what I want to say is the bottom line is brace yourselves a little bit, not a lot. So in these two categories, the most widely used, I shouldn't say most widely used because there's a lot of personal belief going into this listing. But if I want to list out some hardware description languages, some languages include Verilog. I'm sure a lot of you already experienced Verilog at undergrad level or such. This is the most widely used hardware description language in industry. If you go to government work, I've been told that VHDL, the other low-level hardware description language, is also widely used. But if you look at the market share of languages, I think Verilog is pretty much the dominant language overall. It is a relatively low-level language, which is pretty much supported by everyone. It is the assembly, or maybe, yeah, it is the assembly of the hardware description language world. When, say, Intel or AMD designs their next generation processors, a significant portion of that design flow is, I've been told, is done in Verilog. Although in these kind of companies, there's a lot of in-house languages and in-house tools that aid this process. But if you were to design a ASIC chip, if you were to design the next generation processor, a significant portion of that tool chain will be done most likely in Verilog. Other languages, some higher level languages include things like Chisel, which is a Scala-based high-level language which compiles to Verilog. It is a relatively high-level language from Berkeley. It is it's embedded in the Scala language, and it's prominently used because RISC-V, at least initially, was driven heavily by the people at Berkeley. It is prominently used in RISC-V development. Things like the rocket core, etc., is mostly designed in Chisel, I've been told. Another language is Bluespec, which we will be focusing on because I've kind of drank the Kool-Aid for Bluespec already. So yeah, which another language is Bluespec, which also compiles to Verilog. It is another relatively high-level language designed at MIT. It is a strongly typed language which supports types, interfaces, static elaboration, etc., etc. Very high-level language features, which we will talk about in more detail in a couple of slides. Bluespec is also active in RISC-V development with examples including the Piccolo core, etc., etc. And there's a lot of other languages, newly springing hardware description languages, including things like Spinal HDL, MyHDL. There's a bunch with variable levels of adoption, variable levels of efficiency. Some people like to focus mostly on the widely used languages like Verilog. But I think for the purpose, if you have experienced Verilog or VHDL at a class in the past, and at the end of this two-week lecture on FPGA design, and I tell you, oh, go ahead and design a neural network accelerator for Lab 2, if you were to work off Verilog, that would be a pretty hefty task for a half a quarter of work. This is where high-level languages really come in handy. And I think from my experience and my experience with other students that the insight and expertise you get from these high-level languages is actually pretty much orthogonal to which language you use. Things like managing timing, things like managing fan-out and routing. These important topics exist orthogonally from whether your language is low-level or high-level. So I think there is still value, at least in the purpose of this teaching environment. There's a big value in using even kind of niche languages if they are higher level. So yeah, just putting that disclaimer out there in the front. So if we talk a little bit about the register transfer level in the RTL languages and models. So register transfer level languages model a circuit because we are designing hardware. Basically, what we're describing using these languages is a circuit which will be programmed onto a chip. RTL models a circuit using registers, which is state. So state, and combinational logic, which is transfer, or what is describing your actual computation. So yes, registers and combinational logic. Basically, what we're saying is that we're describing a sequential circuit using these languages. So state and transfer. And typically in these languages, of course, this is not a requirement, but when we do programming in these languages, typically everything is clock synchronous because that's just easier to reason about. So if you were to design a actual accelerator at this kind of abstraction, it might look a little bit like this. So here's an example we looked at already in the previous lecture. If you're calculating the gravitational force between two particles, which has mass of m1 and m2, and xy coordinates of x1, x2, and y1, y2, this is what the equation for calculating the gravitational force will look like. And if you were to build a pipeline implementation, pipelining, which we talked about briefly in the previous lecture, if you were to build a pipeline implementation of this function, and we decided to pipeline it three ways. There's three stages: pipeline stage 1, pipeline stage 2, pipeline stage 3, for whatever reason. This could make a little bit of sense, even this kind of division, because this is a pretty much of an aside right now, because this is not the main topic we want to talk about right now. But for floating point operations in hardware, typically multiplication is a little bit simpler. Addition is kind of complicated. Division is very complicated. So it might make sense to have a pipeline architecture, which does, at one stage, does 2 multiplications, and on one stage does 1 addition, and on one stage does 1 division. So this pipeline might actually make sense. So say we decided to design this computation in a 3 pipeline architecture. And we can look at one of these paths. Let's say we look at this path. We take x1 minus x2, label that C, and then we will store C squared into a register D. And the RTL representation for this will look a little bit like this. There are 2 registers, so state, the R part of the RTL, which are x1 and x2, which are state, which should be stored across clock boundaries, because everything is clock synchronous. At the next clock cycle, the RTL portion of doing this equation should be reading register 1 and register x1 and register x2, which should be stored, which should be written to by someone in the previous clock cycle. But at this clock cycle, this portion of the RTL will read register x1 and register x2 to some computation. The transfer part, the logic part, the computation part, the transfer part of this circuit, which is, since we've already read the value for register x1 and x2, we're going to calculate x1 minus x2, and then we're going to square it, and then store it into register D. So this is what we're going to do. So at the end of this RTL portion, we're going to write the value that we calculated. So basically, square of x1 minus x2 into register D. So in this context, if you look at what's happening, x1, x2, and D is state, because x1 and x2 were written to by some other entity and in the previous clock cycle, because everything here is clock synchronous, so clock synchronous digital circuits. So x1 and x2 is state, because we're going to read it in this cycle. And then D is also state, because we're using register D to transfer data to the next pipeline stage. So some other entity decides this RTL portion. C, although, is not state, because it is merely a temporary label given to a temporary variable, which is temporary variable we just calculated as a intermediate value, x1 minus x2. And the value of C will not be written to any state element, which is going to survive across clock boundaries. So this is an ephemeral value calculated by subtracting x1 and x2. It only exists as some electrical signal in some wire. It is never going to be written to a state element such as a register, FIFO, flip-flop, nowhere. So this is just a ephemeral label we're going to give. C is just a label we give to a bundle of wires which exists somewhere in the middle of this combinational circuit. So that's the distinction I just wanted to make. X1, X2, and D is state. They're state, but C is not state, which hopefully clarifies the nomenclature of having state and transfer, registers and transfer levels, registers and combinational logic. Right. And here what happens is that because everything happens at a clock synchronous manner, and we all have to be kind of explicitly aware of clocks and what happens at each clock cycle, this introduces, I think, the biggest hurdle in programmability for doing hardware design, even for FPGAs, which is the unfamiliar constraint of timing. So in a register transfer level representation of computation, the transfer part, the combinational logic part, must finish with what it must start at the beginning of a clock cycle and finish between the end of this one clock cycle. So which means that the logic part, the transfer part, must either have a short enough critical path. If you remember what a critical path is from the circuit, the longest path a signal can take from one of the sources, all of the sources, to the destination. So because here what we're basically doing is calculating D, this critical path will be through reading X1 and X2, through the subtraction operator, and then through the multiplication operator. So if the subtraction operator has a latency of L1, multiplication operator has a latency of L2, the critical path will be something like L1 plus L2. And this must fit within the clock cycle of this circuit. Otherwise, we will not have finished writing to register D before the next clock cycle begins. And when the next clock cycle begins, the next pipeline stage will be reading from register D, which may not be ready when that next clock cycle begins, if the transfer part takes too long to actually transfer the correct value to register D in the previous clock cycle. I'm going to have a visual representation of this in a bit. So if that was kind of confusing because the sentence was a little bit too run on, then it's okay. Anyways, so the logic must have a short critical path, which can fit in the clock cycle, or the clock should be slow enough. The clock cycle should be long enough to fit the longest critical path of any RTL component in the whole design. And that's the part that is the biggest, I think, hurdle in doing hardware design for FPGAs, is that you need to the tools try their best, but the programmer themselves have to be kind of aware of the impact of the code that they write. The impact of the code that they write has on the critical path of each of the RTL levels. And if your circuit results in a slower clock speed, then that across the board results in slower performance and slower throughput, slower everything. So that is a very critical part of your accelerator design, which complicates things. Another thing I want to just quickly point out before we actually get to the language part is quite another hurdle, almost as difficult as, I should say maybe, almost as alien as a concept to at least software programmers as the timing issue is the issue of layout. So here on the left, you see the floor plan, so to speak. The floor plan is the image, visual representation of the components on an FPGA and which components actually use all of them. So each of these little squares, little boxes are the CLBs, the configurable logic blocks with the lookup tables, etc., which we talked about in the previous lecture. And they're, at least in this picture, they are color-coded to represent which of the functional components are using which of the CLBs. So you can see, even if you don't look at what each of these colors are, you can kind of see that each of the functions are kind of grouped together. And people don't do this, compilers do this, but because of the layout constraints and things like that, we're going to talk about just in a bit, they do need to be kind of grouped together, and that adds another constraint on the design that you can do. So all functionality which you write for the FPGA, be it register, state, transfer, computation, anything, all functionality occupies chip space and or resources. Chip space and resources, including things like the CLBs. They're sometimes called LUTs, flip-flop LUTs. They could be using block RAM resources. They could be using DSP blocks for fast arithmetic. But what you write is going to occupy some space. Not everything at the same time, but probably something. If it's doing something, it's going to occupy some resources. And if you write complex enough functionality, it may be difficult to fit it onto the FPGA architecture that is given. For example, you could run out of resource globally if you have no more resources left on chip. If your chip has 500,000 LUTs, if your chip has 500,000 CLBs, and your design requires 600,000 CLBs, then the compiler is going to complain, say the design does not fit on chip. So that's a very real problem that sometimes you run into, although I don't think in the level of complexities we'll be dealing with in places like Lab 2, we won't run into this particular problem, but it is an absolutely serious problem if you're designing complex accelerators for real world purposes. Or if you're designing something like IoT devices, in that case, the constraints are stringent enough that even the little things you build have sometimes having trouble fitting on chip. Another problem is it can run out of resource locally due to placement constraints. For example, on the left, you see here, this is the example of the hard core blocks that I mentioned in the previous lecture. In the zinc chip that this design is using, it has 2 ARM cores in fixed locations on the FPGA. And because these are ASIC blocks, which are embedded onto the programmable logic of the FPGAs, next to the programmable logic of the FPGAs, these things can't move. They're just stuck here. They've been, wired here. They've been fabricated here. When the chip was built, these things can't move. So in this example, for example, if you have too many modules, if you have too many things on the FPGA that need to be near a particular ARM core because they all communicate with that ARM core, for example, or some IO pad, if some pin that leads off the chip because they connect to a general purpose IO pin, because it leads to the host, because it leads to an Ethernet port, for example, if a lot of designs want to talk to that one IO pad, and in that case, due to timing constraints, because it takes time for electrical signals to propagate from, say, that IO pad to that design that needs to be close to it, because it takes time and that signal propagation taking longer time results in a slower clock, the tools will try to put everything that communicates with that IO pad close to the IO pad. And if there's too many of them, and there's other things occupying the space, for example, the tool might not be able to put everything in the close enough location to meet timing, pretty much. Or it might run out of resources. If something like that happens, you might run into a placement issue, and compilation will fail pretty much. We'll talk about more details about this later in the context of actually how to write hardware that suffers as little of these problems as possible, much like how we progress through the GPU topics. But these two, I think, and there's a lot more, of course, because like I mentioned, we are nearing the end of the programmability and versus performance and efficiency spectrum. So there's a couple of problems like this. But at least in my experience working with students, these two seem to be the biggest alien concepts that need to be kind of internalized coming from a software programming background. So these are kind of issues with RTL because we are at some level, we are dealing with the individual transistors pretty much, although we're not dealing with the actual transistors one by one, but we are using a programming abstraction which is very close to the actual physical characteristics of these chips. So one way that people are trying to kind of work at a higher abstraction level so that we don't have to deal with a lot of these things is the concept of, is the topic of high-level synthesis, which is, the other category besides the RTL HDLs. So in high-level synthesis, sometimes called things like C2 gates or high-level languages in general, a compiler translates software programming languages to RTL. There are high-level synthesis compilers from Xilinx and Altera and Intel and a few more places. And typically what they do is they take a C or C++ language, annotated heavily, hopefully, kind of like what you would do with OpenCL or OpenMP, heavily annotated with pragmas. And the compiler takes the C and C++ code and translates into RTL. The theory and history behind high-level synthesis is a complex can of worms that we don't have time to go into. There are classes, graduate level classes here at UCI, which actually deal with this particular topic in more detail, but we won't have time to go into that here. But unfortunately, from my personal experience, for HLS to actually work efficiently, everything needs to be heavily annotated to get the performance that you want. And you actually have to start from a pretty good understanding of the RTL level stuff to begin with, to know what to pragma efficiently. So yeah, that's some people might disagree with this. Some people have, yes, indeed. When I was talking to people, they do disagree with this. They say HLS is pretty good, but at least in my experience, the programmability performance trade-off when using HLS was, I don't think it was worth it for me yet. Which is not to say it might not be good in a couple of years, even for me, but right now that doesn't seem to be the case. An anecdote here is, I think this was from about 2 years ago. There was an engineer, I found a blog online. There are links here if you're interested, although they're all in Japanese. An engineer decided to implement a RISC-V processor using Vivado HLS. And the naive implementation effort, just writing C code that describes the functional properties of the processor and then just measuring the performance, gave it instructions per cycle of 0.0002. For reference, the when running spec marks, modern Intel processors should be giving you IPC of 2 or 1 instructions per cycle. So there's a pretty big difference in efficiency in doing this. And when in the one of the labs in the undergrad computer architecture course that I teach in the winter, one of the labs is to pipeline a RISC-V processor in Bluespec. And by the end of the lab 2, the student built pipeline processors typically do get to something like 0.3. So you can see that there's a pretty big difference in efficiency when you're dealing with high-level languages. And the same engineer actually took a bunch of recommendations for optimizations, where to put the pragmas, how to put the pragmas, etc., and published another post doing as much optimizations as he could. And the resulting IPC is it's much, much better, but still not very good, considering the kind of effort that he put into it. And this kind of matches our, in my research group, kind of matches our experience as well. You need to put a lot of effort into optimizations to get actually good performance, unless your computation is very regular. For example, if you're doing matrix multiplication, I think even without very extensive optimizations, it'll do pretty well. But if you are dealing with very custom, very irregular kind of computation, the kind of stuff that FPGAs are typically very good for, the compilers seem to have a difficult time extracting the fine-grained parallelism from the low-level semantics of a language like C. They have trouble differentiating the intentions of the programmer and the restrictions put on it by the language. And I think this is one of the holy grails of parallelizing programming languages. I mean, this is just such a amorphous topic even to call it a holy grail, but if someone was to design a language that can actually efficiently extract high-level dependencies and fine-grained parallelism from a sequentially written language, that would be a super, super big deal. Anyways, another high-level language that you can potentially use, a software programming language you could potentially use, is something like OpenCL. OpenCL is an inherently parallel language, which can be more efficiently translated to hardware because they are an inherently parallel language, unlike C. And OpenCL compiler infrastructures, OpenCL execution environment, things like that, they do provide a somewhat stable software interface if you use something like an Intel toolchain for compiling OpenCL to FPGAs. So this could be a interesting middle point for writing a hardware. But there is still a significant amount of performance being left on the table most of the times. So That's why in this course, we're going to be talking about mostly dealing with a lower level language, Bluespec. And say you wrote something, the accelerator that you want, on a in either a language, high-level language or a low-level language. Oops. Either you wrote the accelerator in a high-level HDL code, Bluespec, OpenCL, something, or you can write something in Verilog or VHDL, which is a lower-level language. The tool chain would look a bit like this. We're going to be putting more things on this slide as we go forward. So you start with a high-level HDL language, high-level HDL code, and you'll be using something like a language vendor tool, language compiler, to compile it into RTL code, either Verilog or VHDL. Oftentimes, a big benefit of using a high-level language with high-level semantics, not just wires and not just electrical signals, is that some of these languages provide functional simulation, which is when you simulate your code, if you simulate a very low-level language like Verilog, the results of the simulation is pretty much just at every clock cycle, you look at the waveform of the values that are on the individual wires between these modules. It's good, but often if the design is very complex, it's sometimes difficult to make sense of all of this. But the benefit of a high-level language is that if the language toolchain supports a functional simulator, not only is functional simulation because the abstraction level is higher, they don't have to simulate what happens in individual wires on the chip. Performance is typically much better. But also, it supports a lot of high-level debugging functionalities like breakpoints or printfs, for example, which are very useful, and things like that. We're going to be talking about functional simulation in Bluespec also in a bit. But anyways, once you actually do get to the Verilog, VHDL, the RTL representation of the accelerator you want to build, then you make it go through the FPGA vendor tool chain. I say vendor tool chain because there's not a lot of open source offerings for this tool chain. If you buy a FPGA from Xilinx, you'll most likely be using Xilinx tool chains because Xilinx holds the actual architecture of the microarchitecture of the FPGAs pretty close to their chest. So there are some reverse engineering efforts, but mostly you'll be using Xilinx tools. If you buy an FPGA from Intel, you'll most likely be using Intel toolchains. So the internal details of these toolchains are not important for our purposes right now, but typically what happens is that you go through a synthesis step, which you get a net list, and then you do map, place, and route, etc. You go through some toolchain, and you get back what is called a bit file. And this bit file is what is actually sent to the FPGA. And yeah, the purpose of this slide is mostly just to familiarize you with the nomenclature. But the big important thing here is that you get a bit file at the end, which is the description of how the CLVs, how the wiring, how the networking on the FPGA chip it needs to be programmed for the FPGA to function as the accelerator that you designed. Another aside is that another thing that trips new FPGA programmers up a little bit, although for the purpose of Lab 2, I'll be removing this as much as possible. The requirement for this as much as possible is the existence of a constraints file. Constraints file is another thing that a programmer writes typically, which tells the place and route tool, for example, what is the clock speed that this whole thing is running in, by telling the compiler tool, oh, I connected a 100 megahertz clock to pin 2. So assume that the signal coming in from pin 2 is going to be running at 100 megahertz. So try to reason about the timing issues that inside the chip based on the fact that from pin 2, we're going to have 100 megahertz clock coming in, et cetera, et cetera. And other things like if you use DSP blocks, we can also write the constraints file such that we can tell the compiler this particular instance in the code needs to map to this particular location on the chip, the physical chip. But that hopefully we won't do very much. I mean, hopefully, at least for the purpose of this course, we won't be touching the constraint file at all. I just put it here for the sake of completeness. Right. And when we get to the FPGA vendor toolchain, we can also do a cycle level simulation, which is basically what I talked about before as the counterpart to functional simulation. When you run simulation at this level, you can, what the simulator does is actually it looks at what happens at every clock cycle in every single wire and RTL components in the design. So you get a very complex waveform, which is very, very accurate. Most of the times it will be very timing accurate as well in the sub-cycle levels. But it is, you have to look at it at, if something goes wrong at that level. But hopefully in the digital designs we'll be dealing with, we won't have to, at least for the purpose of the labs here, we won't be dealing with this. And I would say if you're designing computation accelerators, as opposed to building things like prototyping platforms, like ASIC prototyping platforms, we normally, hopefully, don't have to deal with this too much. So given this tool chain, we already talked a bit about the various hardware description languages that exist in the efficiency and performance, the trade-off between programmability and ease of use. The analog to the HDLs could be something like if you write something in assembly, you could get more efficiency and performance, but it's difficult to program. Although at this point in software, this is not actually true because most of the times the compiler for C and C++ will be better than you as a person for getting high performance. So maybe this analogy doesn't hold very well. But if you go to the very, very programmable languages like MATLAB or Python, et cetera, you will get a loss of performance compared to C and C++. And Rust and these kind of compiled languages. In the hardware side, that's kind of similar. On the very difficult to use, but high performance, if you do a good job level of languages, you have things like Verilog and VHDL, which are kind of de facto standards in the industry right now. In the middle, you have languages like Bluespec and Chisel and Spinal HDL. And in the right end, you have languages like high-level synthesis, C2 gates, and OpenCL. And the purpose of the rest of this submodule on FPGAs we'll be dealing with Bluespec most, and the lab 1 will also be given in Bluespec. The language itself feels pretty familiar, except for a couple of catches that you need to kind of get used to deal with the peculiarities of hardware. So learning the language itself isn't going to be very hard, at least at the level of the things we're going to deal with for this course. But to get on my soapbox for Bluespec right now for a little bit, just for a little bit. Bluespec, the company, this is an open source language and compiler set. That's one of the big reasons that we're using it. It is a high-level hardware description language without performance compromise, which is good. It provides a comprehensive type system and type checking. It is a strongly typed language, which helps a lot. It supports some high-level functions you would expect and love, things like types, enums, structs, vectors, things like that, which helps your ease of programming quite a bit. It also supports higher order functions like static elaboration, parameterization, polymorphism, kind of like C++ template kind of functionality, which lets you have efficient code reuse and helps you write very, very compact code. I actually love this part about this language. And also it supports an efficient functional simulator called BlueSim. If you use BlueSim, you can kind of work with the hardware design development process in a similar feeling like what you would get from just writing regular software. So that's a big plus. And like I mentioned a few slides ago, I think most of the important expertise is transferable between Verilog and Bluespec. Things like dealing with pipelines, dealing with timing, dealing with placement is orthogonal to the language. So the time spent doing work in this particular language is, I think, will be pretty valuable if you actually decided to jump to a different language down the line. To put a quote by someone that is not me, there's a line of blob of text from a consulting group which reviewed this language. In a comparison with a pretty big language ASIC design, Bluespec demonstrated a 13x reduction in source code compared to Verilog, 66% reduction in verification bugs, equivalent speed area performance to Verilog, hand optimized Verilog, and additional design space exploration within the time budgets. So these are the reasons that we're going to be using this particular language, which is not, although it's kind of a niche language that is not too widely adopted by industry, at least for the purpose of this course. So let's spend just a little bit of time. Unfortunately, I guess we don't have time to go over the whole deck of slides I prepared for Bluespec within this one lecture. So unfortunately, it's going to spill over into the next lecture just a little bit. But let's do a lightning round of the subset of functionalities of Bluespec, at least just enough to do lab 2. So in Bluespec, everything is organized into modules, modules are physical entities on chip, which occupy things like LUTs, CLBs, things like that. Modules have an interface, kind of like imagine the class methods in C and C++. Modules have an interface which other modules can use to access. And the Bluespec model, an accelerator that you will build using Bluespec, anything you build using Bluespec, it consists of a single top-level module, like you see here. It consists of a single top module, consisting of other submodules, module A, module B, etc., etc. And modules consist of state, state and transfer, registers and transfer, state, which are other modules, and behavior, which are represented as rules. This is pretty much the big gist of Bluespec. State can be implemented using registers, FIFOs, memory, things like that. We'll get into a slightly more details about this in a bit. And behavior is described using rules. So this is easiest to look at if you actually look at an example. So if you look at a GCD example, the greatest common divisor example, you take two numbers and you want a hardware accelerator which spits out the GCD for the pair of numbers. And let's say we use the Euclid's algorithm for computing the greatest common divisor. Euclid's algorithm looks a bit like this. So this y-axis is time. As we move down, time moves forward. We have x and y as input. Let's say x is 15, y is 6. And the Euclid's algorithm uses two rules or two disjoint behaviors to calculate GCD. So this is the example. If x is larger than y, we subtract y from x. That's the first rule. Because in the input, x is larger than y, 15 is larger than 6, we subtract 6 from 15. So we get 9 at x. So it's 9 and 6. X is still larger than y. It is 9 versus 6. So we're going to subtract 6 from 9 again. So the next cycle, we get 3 and 6. But now x is smaller than y because 3 is smaller than 6. And when that happens, we don't subtract, we swap. So that x is now 6 because y was 6 before. And y is now 3 because x was 3 before. And now x is again larger than y, so we do subtraction. And now we get 3 and 3. And the condition shouldn't be x is larger than y. It should be larger than or equal to y. So when x and y is the same, we do subtraction again. So x becomes 0. And when x becomes 0, the answer is the value in y. So now we know that between 15 and 6, the greatest common divisor for 15 and 6 is 3. So this is Euclid's algorithm for calculating the greatest common divisor. And we can try to design a hardware accelerator for calculating this in a, hopefully a not a highly performant way, but we can build a hardware accelerator for calculating this. And the whole code looks like this, and we'll walk through this step by step. The whole code consists of state, behavior, so RT, state and behavior rules, and the interface, which is also behavior, the interface the outside module uses to communicate with this particular module. So let's look at things one by one. We have a module called make GCD, greatest common divisor. This is just a name we gave it. And it consists of submodules for storing state. And these particular submodules used here are pre-provided by the language, register, and FIFOs. So the lingo is maybe a little bit complex, but what it does is actually quite simple. Module make reg, mkreg, is using an interface reg, and the type parameter given to it is an int30. It's a bit 32. I should fix that. Module parameter is 0. So module parameter given to the instantiation is 0, make reg 0. And the register has a type parameter bit 32. And what these parameters given to the types and the modules, how they actually impact the actual circuit that is generated is dependent on how the individual modules are implemented. But at least for the purpose of these, in the context of these pre-provided modules, when you do a register of type bit 32, it is basically saying we instantiate a register that can store a bit 32 type. And this register initial value is 0. Same here, and the register is called X. Similarly, we have a register Y, which is a register of bit 32 type, initialized to 0. And we also have a FIFO. FIFO F. FIFO F is slightly different from, there's a different thing called FIFO as well, but right now this isn't important. So let's say we have a FIFO F. Also, this is a FIFO, which means it's a queue. You can push it in one end, you can get the results out in the other end. So you have a hardware queue of type bit 32 called out queue. And it is a sized FIFO F of size 2. Out queue has a module parameter 2. And in this mixed size FIFO context, 2, when you give it 2, you basically say build a fixed size FIFO of size 2. And the fixed size nature of FIFOs here is also kind of interesting if you're coming from a software designing background. Is that if, for example, if you use a queue or a vector or a list in STD or standard template library or something like that, or software queue or something like that, the size is typically, you don't need to care explicitly most of the times about the actual size of this queue. When you push more things in, it allocates more memory for itself. And it just works kind of well unless you run out of memory. But in the hardware context, unless you are also building something complex, which uses off-chip memory or block RAM or things like, even when you use block RAM, each of these slots in the queue for out queue is taking up explicit resources on the chip. It is taking up LUTs, it is taking up CLBs, etc. So if you give it a size 2, you only have size 2. It's not going to reallocate more memory for itself while the accelerator is running. Once it's compiled with a size 2, that's all the size that it has. If you try to put more things into it, something bad could happen. I mean, the language prevents you from actually putting more things into this, but this is the size that you get. So anyways, in this module, we have 2 registers, X and Y, and a FIFO called outQ. And there are 2 rules, step 1 and step 2, which actually does computation using these state elements. And you can see that these are called rules. Rule step 1, rule step 2. Rules are atomic transactions, and they do what is called they fire whenever a condition is met, and the condition is called a guard. This is the, I think the biggest lingo that you will, this is the biggest and most important new lingo. So you have step 1, rule step 1, which is if x is larger than y, and if y isn't 0, this needs to be here. Comparing y to 0 needs to be here in case so that these rules don't fire when we don't actually have input, because the input data was 0. The initial value for x and y were 0. And maybe I should first point out that what rules do is that I mentioned that they fire whenever a condition is met. And one of the operating words is that whenever. If the guard is met, it's just going to fire every single cycle. If x is larger than y, if y is not 0, this computation, swapping x and y pretty much, is just going to repeatedly fire forever. Every single cycle is going to fire as long as the guard is met. So you have to organize the guard such that it actually describes the behavior that you want. So if x is larger than y and y is not 0, we swap. In a different rule, if x is smaller than or equal to y, which is disjoint from rule 1, and again, if y is not 0, we subtract x from y. The name here has been, unfortunately, x and y has been swapped from the previous example, so hopefully it won't be too confusing. But anyways, and if y minus x is 0, we enqueue the results into outqueue. And this might be feel kind of strange if you think about it. We're subtracting x from y and then putting it into y. And we're using these funny arrow notations. If you're familiar with, if you use Verilog, you will probably be used to this. This notation will probably be familiar to store something into y. But instead of checking if y is 0, we're checking if y minus x is 0. And then we're pushing x into outqueue. The reason for this, we'll hopefully have more time to go into in a bit, is that for each of these state labels, x and y and outqueue and all these things, the values that these names, these variable names, x, y, and outqueue represent are fixed to the values that they had at the beginning of the cycle, when the clock cycle first started. So, and the state changes that happens in these rules are only applied semantically at the end of this whole clock cycle. So even if we had a statement here that says we assign some value to y, the value for y is not actually changed until after this rule has finished executing. So if we write, say, for example, when this cycle starts, y was 4, x was 2. After this cycle finishes, y will have a value of 2, 4 minus 2. But while this rule is still executing, y will still have a value of 4, x will still have a value of 2. So another example, if y is 2 and x is 2 as well, and we want to check, because y minus x is going to be 0, we want to send the results of x to the output queue. But if we didn't compare y minus x equals 0, if we just compared y equals 0, because for some reason we didn't know about that characteristics of the language, or in hardware design in general, the y equals y minus x, the effects of this will not be visible to this line yet. So even though y will turn out to be 0 after this cycle, this if statement will actually not fire. So that's why we need to compare y minus x equals 0, as opposed to if y equals 0, because the effects of this subtraction will not be visible to this if statement within the same clock cycle. Yeah, this is one of the things that kind of trips software programmers up a lot. And this is going to come up, this similar topic is going to come up repeatedly. So yeah, so that's that. And then we get to interfaces. Interfaces are like class methods. They're analogous to class methods that you should be used to in C, C++ and Java. You can either have, we're going to have a chance to talk about this a little bit more detail in the later sections, but you can have an action method, which takes one or more arguments, 0 or more arguments actually. This particular one takes A and B as arguments, which you will set to X and Y. Yeah, action methods take some input and then apply some change to state. That's what they do. We can also have an action value statement, which takes some arguments or not. This one doesn't take any arguments, and then returns a value. It returns this particular one returns a bit 32 value. It takes a return value. So here we have two functions, start and result. And yes, there's a question, if you write another rule called step 3, which writes the if statement as part of its guard, yes, that would work as well. Although it might create some change in the total number of clock cycles it takes. Yeah, that's an interesting thing you could do as well. Anyways, so here we have the start method and we have the results method. Start is only, so interface methods are also atomic transactions, meaning they also have guards and they can be only called when their guards are also satisfied. And because these interface methods can only be executed, they can only be called by rules in the outside module. When a guard for the interface method is not satisfied, for example, if Y is not 0, if there's a rule in the outside world which tries to call start, that whole rule will not fire. Because, again, because these are transactions, because rules are atomic and rules are transactions, the rule does not fire unless all of its guards are met and all of the guards for all the methods that it calls. Unless all of them are met and all of them can actually be applied, the rule does not fire. So when a guard is not satisfied for a interface method, rules that call it also cannot fire. So if there's an outside rule that tries to call start to enqueue a piece of work into this accelerator, unless what this Y equals 0 is basically saying is that unless this module is idle, unless the computation is done, this rule is not going to, this method is not going to be callable. And when the computation is done, remember that we push the output results into outqueue. And there's a method called result. If someone the outside world will be polling pretty much this result function, there's going to be a rule that tries to call this function at every given cycle, although it might not be able to call it every cycle because of the guards of its subcomponent, for example. What this in this example, what this is doing is it's calling out q.dq and then returning the output q.first, which is the first element in the FIFO. And this is another thing that trips up some people. I think the language could actually be designed to kind of make this more familiar to software programmers, but the designers decided not to. Some people might be confused because we're calling dq first and then returning the output.q. So it feels like we'll be dequeuing the result, one of the results, throwing it away, and then returning the next value. So it feels like this code kind of can be read like we're going to have wrong results. But in this example, at least, this is okay. Because if you remember, each rule, each method, all the state labels represent values from the beginning of the clock cycle. And the effects of each method, the effects of each rule firing will only be applied at the end of that clock cycle. So outq.dq, the effects of this will not be visible to this return statement until at the end of this method call. So even if we called outQ.dq first, the value that outQ.first will return is the first element in the queue before outQ.dq was actually called. This might feel a little bit confusing, but just remember, this feature is pretty much the same for most HDLs out there, unless you're working with high-level synthesis. This is the same for Verilog, for VHDL, for Chisel, for everyone. The effects of a statement is only visible to anyone else after the end of this block finishes. At the end of that particular clock cycle, after the end of that particular clock cycle, the effects of any of these statements become visible to the outside world. Yes, so this simple design is possible of calculating GCD. The outside world can call the start method and the result method to control what happens inside this module. And once you give some parameters as input, it will do the work diligently using Euclid's algorithm and then spit out the results via the result function. One potential caveat of this is that the latency of computing this is variable. And I don't know if for this particular algorithm, we can make the variable latency fixed, for example. If you give a very large number to x and y, or a very large number to x and a small number to y, for example, this algorithm could be taking hundreds, thousands, millions of cycles to finish. And if you instantiate just one of these modules on your FPGA accelerator, I don't know if it's going to be any better than if you just wrote it in software. I think just because this is pretty much a sequential algorithm, if you were to instantiate one make GCDs in your accelerator, you probably won't get any performance benefits compared to CPU. Because it is a sequential algorithm, it's pretty much doing the exact same thing your CPU would be doing, maybe. But the benefit of a potential benefit of doing it here in the FPGA could be just because the design of make GCD is so simple. If you had an application which is heavily reliant in terms of performance for calculating GCD, you could potentially stamp out hundreds of these things as much as it would fit on the chip, hundreds of these things on an FPGA and parallelize the work if your application supports it. And that's one way you can actually get high performance out of this. Right. So yes, there's a question: how do the rules fire when the start action is called? In this example, particular example is slightly simpler because the guard for start is y equals 0. And the rule step 1 and step 2 says y equals not 0. So the guards for the two rules and the start method is disjoint. They're mutually exclusive. So when start can be called, rules will not be firing. If rules are firing, start can't be called because y would not be 0 if the rules are firing. Start can't be called because start needs y to be 0 for the outside world to be allowed to execute this. Things may become a little bit more confusing if these guards are not mutually exclusive. When that happens, Bluespec compiler actually instantiates what is called a scheduler, so that when two or more rules can fire at the same time, but they conflict with each other. We're going to talk about what conflicting is in a bit. But if two rules are conflict with each other, these start and say step 1. If the guards overlap, they could conflict with each other because they're both writing to the same register, x and y, x and y. So if the two rules, for example, let's say, for a simpler example, let's say maybe step 1 and step 2, the guards may not be mutually exclusive. In this example, they're absolutely mutually exclusive. Let's say they're not, and they both try to write to the same register. That wouldn't make sense in the hardware context because at the end of the cycle, each register should have a value, but these two rules will be describing different computation, different values that should be written to each of these rules, each of these registers as a result. When that happens, Bluespec instantiates a scheduler that picks just one rule per clock cycle among all the rules that wants to fire. If they conflict with each other, picks one rule that will fire at any given clock cycle, so that this kind of weird conflicting behavior doesn't actually manifest. Yeah. You probably have some time a chance to go into a little bit more detail about how all that works later. It's one of the things that actually simplifies design using Bluespec quite a bit compared to languages like Verilog. But yeah, that's basically what happens. If a bunch of rules, if 10,000 rules, if you write 10,000 rules and none of them conflict with each other, all of them are either pipelined or they're completely parallel, 10,000 rules will be firing it at every given cycle. And that's where the parallelism comes in. If you are able to express the computation that you want to do in terms of, in an extreme case, 10,000 rules, and every single cycle, 10,000 rules are firing, doing some kind of computation, you will have a parallelization factor of 10,000. That's where the big performance improvement comes in. The difference between rules and interface is rules are kind of autonomous, so to speak. They, whenever guards are met, they just fire on their own. Methods needs to be called from the outside world. So output.dq is a method. It needs to be called output.enqueue is a method, but it can't execute on its own. Another outside rule, for example, step 2, needs to call outqueue.enqueue to put some data in. You could call outqueue.first. This might not be a very good example because results in also a method, but you could have a rule 3, for example, which calls outqueue.first. And outqueue.dq, which also interacts, which is also calling the methods of the output queue module. But anyways, these methods enqueue, dq, and first can only be they can't execute autonomously. They need to be called from the outside world. They need to be called by a outside rule. Rules can execute autonomously whenever their guards. They will execute autonomously whenever all of their guards are met. But methods are, if no rule explicitly calls a method, that method will never fire. It's just sitting there. So basically, one potentially wrong abstraction to imagine this is basically to think of rules, each rule as a thread, which is just looping forever to see if there's something it can do. And methods are functions called by these threads. Yeah, that's a potentially wrong abstraction, but it might help imagine what these things do. Rules are each individual rule is each individual thread. All it's doing it's like the loop statement if you write something in Arduinos, for example. What rules do is just say loop forever, checking repeatedly if all of their guards are met. If all of their guards are met, they do some work. And some work might include calling a method of some different module. Right. So yes, with these examples in mind, I hope that was a very high-level example. With these examples in mind, I'm going to go spend a little bit of time. I was hoping that I'd be able to go through all these slides today, but that may have been a little bit of hubris on my part. But we're going to go into just a little bit more detail about the language features, because that's the language we're going to use. For other questions, language-specific examples, questions, you can also ask me, or if you're so inclined, you can look for PDF books which are available online, PSV by example, or Bluespec reference guide for more details. But anyways, the keywords that are the action words, the operating words when you're dealing with Bluespec and HDLs in general is, first, you have a bunch of modules with interfaces. And you also have rules with implicit and explicit guards. We'll go into a slightly more detail about what these things are in a bit. And after we're done with Bluespec, at least some facets of Bluespec, we're going to use this as the description tool for talking about how to build efficient FPGA.